Hey guys! What's up? My name is Johnny Ezekiel Gulmatica and today we're gonna talk about the nature's number. So, let's go!
It has become conventional, as I have noted, to separate mathematics into two distinct subdisciplines labeled pure mathematics and applied mathematics. This is a separation that would have baffled the great mathematicians of classical times. Carl Friedrich Gauss, for example, was happiest in the ivory tower of number theory, where he delighted in abstract numerical patterns simply because they were beautiful and challenging. He called number theory the queen of mathematics, and the poetic idea that queens are delicate beauties who do not sully their hands with anything useful was not far from his mind. However, he also calculated the orbit of Ceres, the first asteroid to be discovered. Soon after its discovery, Ceres passed behind the Sun, as seen from Earth, and could no longer be observed. Unless its orbit could be calculated accurately, astronomers would not be able to find it when it again became visible, months later. But the number of observations of the asteroid was so small that the standard methods for calculating orbits could not provide the required level of accuracy. So Gauss made several major innovations, some of which remain in use to this day. It was a virtuoso performance, and it made his public reputation. Nor was that his only practical application of his subject. Among other things, he was also responsible for major developments in surveying, telegraphy, and the understanding of magnetism. This chapter deals with a case history of just such a development, whose most powerful application is television, an invention that arguably has changed our world more than any other. It is a story in which the pure and applied aspects of mathematics combine to yield something far more powerful and compelling than either could have produced alone. And it begins at the start of the 16th century, with the problem of the vibrating violin string. Although this may sound like a practical question, it was studied mainly as an exercise in the solution of differential equations. The work was not aimed at improving the quality of musical instruments. Imagine an idealized violin string, stretched in a straight line between two fixed supports. If you plug the string, pulling it away from the straight line position, and then letting go, what happens? As you pull it sideways, its elastic tension increases, which produces a force that pulls the string back toward its original position. When you let go, it begins to accelerate under the action of this force, obeying Newton's law of motion.